Chapter 4 is all about something called Gauss's Law. Now we can remember that no matter what, we can always use Coulomb's law, F equals K Q prime times Q divided by R squared, in combination with the definition of the electric field, E is equal to F divided by Q. We can always use this process to find what an electric field is. No matter what, this will always work. But it's not always easy. Think about the integrals from chapter 23. It can be very tricky to find what the electric field is using the definition of Coulomb's law. This is where Gauss's law comes into play. Gauss's law is an approach to find an electric field so we can find E if the charge in your question is symmetric. So we have nice symmetrical charge distributions. And if this is the case, we can use Gauss's law to find electric fields. It's very easy to use, it's just a little abstract. So to understand Gauss's law, first we need to introduce some concept. So the concept known as electric flux. So the electric flux has a specific definition, and it's the perpendicular portion of an electric field that passes through some area. What does that look like? If we draw an electric field, that goes parallel to the horizontal direction. So here's my electric field, and I'm going to put maybe a sheet of paper, a metal sheet inside of this electric field. I'm going to put it in at some angle. Now the size of this sheet, it's in 3 dimensions, so it has some surface area, some area that the electric field is passing through, so that's going to be A. That's my area. I have my electric field E, but I don't want the whole electric field. I want the perpendicular piece of that electric field. So what I have to do is draw perpendiculars to this area. So I put in a right angle and draw pieces that are perpendicular. So my blue lines are perpendicular to this area, so that makes right angles with that little area, and I'm going to call those E perpendicular. So I'm figuring out the projection of the electric field in the perpendicular direction to this area A. So each of those fields is perpendicular, and I need to figure out what this is. I need to know what is this perpendicular piece. So to do that, I can draw in my right triangle. Drawing a nice little triangle in here. I have my perpendicular here. I have my hypotenuse is going to be equal to this horizontal segment. That horizontal segment is just my electric field E, and I'm interested in what this perpendicular piece is. What is E perpendicular? If my angle here is theta. So I can see using trigonometry that the E perpendicular that I'm looking for is equal to E times cosine of theta. And then I can see that my electric flux is equal to the electric field that's perpendicular that passes through an area. So I'm going to multiply it by the area that it passes through, and I get my final definition for electric flux. Flux is equal to E times the cosine of the angle times A. And that is the definition of my electric flux. And we'll see a little example in class, and I'll talk about this a little bit in class to try to make it make a little more sense as well. So the concept of the electric field and the electric flux is that the flux is the number of the field lines that pass through some surface that you put inside of that electric field. So I've drawn an electric field here. This is one electric field, and these are the field lines. I have 4 different field lines for this field. And I'm taking this sheet of paper, whatever I'm putting inside of this field, and I'm putting it in 3 different orientations. I have it straight up and down, I have it kind of angled a little bit, and then I have it parallel to my field. Another way to think about that angle that we just talked about, that cosine of the angle, to find the perpendicular field. We can also think about that as selecting out the perpendicular piece of area. So what we need to do is figure out what is the direction for an area. This is kind of a strange concept, but the direction of an area is always perpendicular to your surface. So in this first case, in case number 1, the direction of my area vector, if I was drawing a direction for the area, would be perpendicular to my surface. I can do the same thing for plate number 2. My area is going to point up at some angle to get me perpendicular to my surface, and then my third area is going to point straight up, again perpendicular to my surface. So these are drawing out the directions of my area. And in that definition for flux, where the electric flux, phi, is equal to E times A times cosine of my angle, this angle right here is the angle between my electric field and my area direction. So I can figure out what that angle is for each of these cases. If I look at my first case, case number 1, the angle here between A and E is equal to 0. They're both going in the same direction. So my phi is going to be equal to E times A times cosine of 0, which is just equal to 1. So phi is going to be equal to E times A. And we can compare this to case number 3, the other extreme case. Theta, in this case, the angle A is perpendicular to my field E. So theta is equal to 90. And my phi, my electric flux, is equal to E times A times cosine of 90, which is 0. So the electric flux, in this case, is 0. And I can conceptually see that where I have no field lines. There's no lines passing through this third surface. Then I take the in-between case. Theta is some angle, we don't know what that angle is, it's just some angle between 0 and 90. For the sake of argument, we'll say it's 45. So my flux is equal to E times A times cosine of 45, which is some number between 0 and 1. If you plug it into your calculator, you'll actually find that cosine of 45 is 0.7. So we can compare the number of lines that pass through our case number 1 with the number of lines that pass through case number 2. Case number 1 has E times A lines. Case number 2 has 0.7 times E times A. So case number 2, when I'm at an angle inside of my electric field, has to have fewer lines than case number 1. And if I compare the number of lines, in case number 1, I've got 4 different lines. In case number 2, I've got 2 lines. So it conceptually works out. As I move my area, as I rotate my little shape, so that less and less of it is inside of this electric field, so that fewer lines are passing through it, I get a smaller and smaller electric flux. Now if I have multiple surfaces inside of a field, then I can figure out the total flux in that situation as well. The total flux is going to be equal to E dot A. This is a dot product, so remember that implies we still have that cosine in there. That's what the dot product is. It involves the cosine. And I add in this summation. So that just means I sum up the fluxes from all of the surfaces that are inside of my field. So the total flux is the sum of individual fluxes. If, however, the shapes are weird, and it's not easy to add up the individual fluxes, then I need to turn to calculus. I turn to calculus in the form of electric flux is going to be equal to the integral of E dot dA, which your book will also maybe be written as the integral of E perpendicular times dA. In this case, that dot is very important in the first part because that implies that this is a dot product and you're using the cosine. In the second definition, this E perpendicular, I haven't written that dot because the perpendicular piece assumes that dot intrinsically. This situation that we have, this thing, works for what we call an open surface. This means that the surface isn't closed up. It's like an open box instead of a completely closed box. And in this case, the sign of the flux can be chosen. I can pick whatever direction I want to be a positive flux as long as I choose the opposite direction as being negative. So what does that look like? Let me say I have an open surface, so it's not closed off, it's just a sheet just sitting here. I can say that my flux, if my field line is passing through and going to the right, I can define that flux, we'll call it flux number 1, as being positive. But if I do that, then any flux, any electric field that sets up a flux in the opposite direction, so in this case flux 2, which is going left, is going to be a negative flux. Okay, so this is very important to note for electric flux of an open surface. Now, what does the electric flux of a closed surface look like? So for a closed surface, we have something that looks very similar. The electric flux is equal to the integral from E of E dot dA with this little circle thing here on the integral. This circle thing means that my surface is what we call closed. Otherwise, it looks exactly the same as an open integral, as an open surface. So this is a closed surface. So this is like a closed box of some sort. So let me try to draw a box. And this is in 3 dimensions. There's my little 3-dimensional box. And it's closed off. It's a closed box, so the distinction between an open and a closed surface comes from picking the sign. In an open surface, you can pick whatever direction you want. With a closed surface, your electric flux is going to be positive if it's coming from inside the box. Inside of whatever your surface is. So I can draw positive field lines as long as they start on the inside of this box and come to the outside. So that would be a positive flux. The line can come out to this side. It would be positive flux. As long as it's starting inside of the box, it's a positive flux. Conversely, a field is negative if it's coming from outside the box. So if your field is penetrating into the box, into the surface, if it's coming from outside and going in, then it's going to be a negative field, negative flux. So I have a line field that starts out here and penetrates into the box. That's going to be a negative flux. And I have a field coming into the box. That's going to be a negative flux. So if coming from the inside and going outside, you are positive. If coming from the outside and going inside, you are negative. That's the distinction between a closed surface and an open surface. To get a little bit of practice with this, I would suggest looking at checkup 24.1 and read over example number 2. So now that we know what electric flux is, we can get to the real goal of this chapter, to learn and understand Gauss's law. And Gauss's law says that if a closed surface, so this is a closed surface that we're working with, has some charge inside of it, some charge called Q inside, then the electric flux has a very specific answer. The electric flux for a closed surface, we already know, is equal to the integral across that closed surface. Remember, that little circle means our surface is closed, of the electric field times the area of that surface. And Gauss's law tells us that this is equal to the charge inside of that surface, the charge that's enclosed, divided by epsilon naught. So this right here is Gauss's law. The electric flux, the closed surface integral of E dot dA, is equal to charge inside divided by epsilon naught. And it works if you have a closed surface and a whole lot of symmetry. When you're applying Gauss's law, the surface that you use to enclose your charge, and remember, this is a closed surface that you're using. The surface is called a Gaussian surface. It can be a real surface that's given in the problem, or it can be one that you imagine enclosing all your charge. It can be real, or it can be imaginary, something that you put into the problem to make it easier. To get some practice with this concept, you will really want to read up and make sure you understand the questions in checkup 24.2. So we're going to work with Gauss's law a good bit, and you're going to have to do some practice problems on your own. And as you read and study the chapter and do these practice problems, something that isn't quite clear that I'd like to explain a little bit more is how you use the different charges, how you get all these different Q's in various situations. So if you're working in one dimension, typically this is charge spread out along a line. Your charge is going to be equal to lambda times L. This should look familiar from previous chapters. If you're working in 2 dimensions, your Q is going to be sigma times A. In 3D, your Q is going to be rho times V. I'll do one example for you to try to make this a little bit more clear so you can see what's going on, and then we'll move on. So the example I'm going to work on is figuring out what is the electric field from a single point charge. So I'm going to draw a single charge. I want to know what is the electric field at any position. So I'm going to pick some position right out here. That position is going to be a distance r away from my charge. And what I'm going to do is I'm going to draw a circular shape around this charge. This circular shape, you can actually think of it as a sphere, if we can think of it as a 3D object. It's a 3D ball that's enclosing all of this charge here, all of this Q. So this red shape I've drawn is a Gaussian surface. Okay, so if I have a Gaussian surface, then I know from Gauss's law that the electric flux is equal to the closed surface integral of E times dA, which is equal to Q inside divided by epsilon naught. Now, if I look at the field that this is drawing, I know what the field looks like. I know the field for a positive charge points away, so I have a field that's pointing away at all points. So this field is very, very symmetric. This tells me that I can use Gauss's law, and it also tells me that the electric field that I have can be pulled out of this integral. The electric field doesn't depend on this area. So the electric field comes out, and I have a closed surface integral over the area of my Gaussian surface is equal to Q inside. The charge inside of this red surface we can see is just equal to that little charge Q, that single point charge. All that divided by epsilon naught. So now the only thing left here is to figure out what is this surface integral, this closed integral over my area dA. So what is the area of a sphere? What is the area that these lines are passing through? That's just the surface area of a sphere. I integrate over the surface area of a sphere, and I find 4 pi times r squared. I'm integrating over the area of this Gaussian surface. And by doing that, it's just the surface area of a sphere, 4 pi r squared. And that's going to be equal to Q divided by epsilon naught. This gives me that E is equal to the charge divided by 4 times pi times epsilon naught times r squared. I did this all using Gauss's law. The key in Gauss's law is understanding how this surface translates into being the integral over dA to give us 4 pi r squared. To get a handle on that, you really just need to solve a lot of examples. So that's why I'm suggesting that you look at and try to understand and practice, try to do these yourself, examples number 4 through 10. These are well worked in the book. I'm happy to work over them on class. One of these will be on your quiz. So if you have questions and don't understand how they work, then ask me questions. Send in questions 2 days before we cover this in lecture, in class. Because one of these will appear on your quiz, numbers 4 through 10. So really try to understand how this surface dA, how this integral over dA, the integral over this surface, this red sphere that I drew to encompass this charge, gives me my 4 pi r squared. And the really neat thing here is that this should look very similar. 1 over 4 pi epsilon naught is k. They're the same thing. That's what k was defined as back in chapter 22. So this is just equal to k times q over r squared. This is something we already knew, something we already solved using Coulomb's law. Just a little bit easier using Gauss's law once we understand how this integral dA gave me this 4 pi r squared. This part, understanding this, will be key, so make sure you practice those examples 4 through 10. Ask me questions if you don't understand them, because one of these will be on your quiz. So the last thing to talk about in this chapter is what happens when we put a conductor inside of an electric field. Now we know that for conductors, charges move really, really easily. Charges are happy to move along conductors. So if we put a conductor in an electric field, what is going to happen? Charges, it turns out, when you put a conductor in an electric field, all of the charges will spread evenly along the surface. They align themselves with the electric field and spread themselves evenly. And this even spread means that the electric field inside the conductor cancels out the electric field outside, so the electric field inside becomes zero. The electric field inside of a conductor inside of some kind of field, the electric field inside becomes zero. Inside of a conductor, you have no electric field. So if we look at what this means for the charge inside of a conductor, the integral closed off of E dot dA, Gauss's law, is equal to Q inside of your surface divided by epsilon naught. So if the electric field inside the conductor is zero, E is equal to zero, then that means that Q inside over epsilon naught is equal to zero. Since epsilon naught is a constant, is always a number, this means that Q inside of a conductor is zero. The total charge resting inside of a conductor is equal to zero. And the last thing this means is that all electric fields for a conductor, all the electric field lines, point away from the conductor and they point away perpendicularly. All electric fields are perpendicular and point away from a conductor. Okay, so my last piece of advice for you as you're going through this chapter and trying to understand Gauss's law is to read and study and apply the problem-solving techniques on page 777, which is all about using Gauss's law for charge distributions with symmetry. I'll make the suggestion once again that for Gauss's law, which tells us that the flux is equal to the closed surface integral of E times dA being equal to Q inside over epsilon naught, the real key thing to understand is that integral over dA. Good luck, and make sure that if you have questions, you send them in to me.